Hello everyone, welcome back to the Chanel. Today we're taking an in-depth look at one of the most talked about systems to emerge from the conflict, the so-called pot-bellied weapon. This is not some clickbait nickname. The shape and profile of the platform earned it that label because it departs from conventional, sleek cruise missile silhouettes, and instead presents a stout, bulbous body that carries a suite of capabilities packed into a deceptively simple form. I'll walk you through how it looks and why that matters, what's inside, briefly, how it performs on the battlefield, what safety measures have been engineered into it, the features that make it stand out from other systems, an estimate on cost and logistical implications, and finally, what this means strategically. The goal here is to explain clearly so you can understand why this system has caused so much attention and why defenders find it difficult to stop. At first glance, the exterior is arresting because it's unconventional. Squat, rounded, and almost squat-bellied compared with the slender fuselage of classical cruise missiles. That chunky midsection is purposeful. It houses a larger internal volume for fuel, electronics, and modular payloads while maintaining a low, radar-deflecting profile. The outer shell uses composite materials and angled surfaces, and you'll notice a low-mounted sensor array and folding control surfaces that reduce detectability when cruising close to terrain. The airframe appears optimized for low-altitude, terrain-hugging flight. Its wings are short but wide, providing lift at low speeds while allowing quick bursts of maneuverability. There's modest exhaust shielding and a muffled intake design, which together reduce thermal and acoustic signatures. On the exterior, there are also provisions for quick reconfiguration. Hardpoints and access panels that let ground crews swap payload modules or electronic warfare packages in the field. Paint and coatings rely on muted matte tones, with thermal dissipative properties rather than conspicuous camouflage, and the whole package is compact enough to be transported on smaller vehicles and launched from improvised platforms if necessary. In essence, the outward design prioritizes survivability through low observability, modularity for mission flexibility, and logistics simplicity, so a force with limited institutional resupply can still operate it at scale. Inside, compact engineering tells the same story. A tight electronics backbone, a small but efficient propulsion bay, and modular payload bays that let operators choose warhead or mission equipment. The control logic is focused on autonomy and redundancy. Navigation, guidance, and power systems are stacked and shielded to tolerate jamming and rough handling. The interior is short on frills and long on functional packing. Every cubic centimeter is used to balance range, payload, and electronic resilience. Performance is where the design choices start to pay off. The platform is optimized to fly low and slow enough to trick conventional radar and fast enough to reach targets hundreds of kilometers away. It's not built for supersonic dash speed. Instead, its advantages come from a mix of persistence, low-altitude flight profiles, and intelligent routing. The guidance suite combines inertial navigation with terrain-following algorithms and occasional satellite updates, and crucially, it has fallback modes that allow it to navigate using onboard maps and visual landmarks if external signals are denied. In practice, that means the weapon can reroute when air defenses light up, approach from unexpected vectors, and perform small, unpredictable maneuvers in the terminal phase to complicate interception. Propulsion-wise, it uses a compact turbojet or small turbofan with good fuel efficiency at subsonic speeds, enough to maintain the profile needed for low-altitude penetration while keeping thermal output manageable. Observers have reported that swarms or coordinated launches of these platforms exploit saturation effects. Rather than trying to intercept every single unit, defenders are forced to pick which threats to engage, and the remainder get through by sheer numbers and clever flight patterns. In addition, because the platform can carry different payload types and detonate precisely, it is effective against command nodes, air defense radars, logistical hubs, and hardened structures when used in concentrated waves. Its endurance and reach, combined with a relatively cheap unit cost, fundamentally change how attrition trades are calculated on the battlefield. Safety measures are surprisingly considered for a weapon designed to be lethal. There are multiple fail-safe protocols embedded in the control firmware to reduce the chance of accidental strikes or recovery by unintended parties. For example, if the platform loses target confirmation or detects a predefined no-go electronic signature, it will divert to a pre-programmed SEU FIDE. What makes this platform uniquely potent are several selling points that go beyond its physical silhouette. First is modularity. The ability to swap warheads and electronic payloads quickly allows a single airframe to do multiple roles across missions: strike, suppression, electronic attack, or even deception. Second is cost efficiency. The components use domestic supply chains and commercially available manufacturing techniques, meaning they're cheaper to produce in volume than many imported or high-end systems. That allows a force to field dozens or hundreds rather than single digits. Third is survivability through simplicity. The combination of low-altitude routing, a compact thermal signature, and autonomous fallback navigation makes traditional layered defenses less effective, especially when facing coordinated launches. Fourth is adaptability to asymmetric employment. These platforms can be launched from road mobile systems, rail spurs, or coastal batteries rather than requiring advanced fixed infrastructure, which complicates targeting and preemption. Fifth, the design philosophy emphasizes rapid iteration. Feedback from field operations is incorporated quickly into hardware and software updates, enabling the platform to evolve in near real time. Taken together, those features change the calculus for both attackers and defenders. Instead of relying on a few high-value, high-cost missiles, an operator can afford saturation and smart targeting, while defenders have to invest in more sensors, more interceptors, and more complex decision-making logic to respond effectively. Price is always a sensitive subject, and exact figures are usually classified or estimated. What's clear is the platform's economic model: prioritize domestic production, simplicity of parts, and modular payloads to bring per-unit costs down relative to traditional cruise missiles. That means a single operationally effective unit costs a fraction of a high-end Western missile, but crucially, still packs enough capability to destroy high-value targets when used en masse. The downstream implications are strategic. Low unit cost plus modularity means operators can sustain pressure over time rather than spending their inventory in a single decisive volley. From a procurement standpoint, this changes budgeting priorities. Spend modestly on many intelligent units rather than heavily on a few expensive systems. Logistics ease, transportable on light trucks, launchable from improvised sites, also reduces the hidden costs associated with fielding and maintaining a high-tech strike force. In short, the price-performance ratio is what really gives this platform an operational edge. You get credible, adaptable strike capability without the long-term financial drain associated with exclusive reliance on imported high-end munitions. In conclusion, the Potbellied platform is less about a single technical breakthrough and more about a new approach to match capability to strategic reality. It demonstrates how smart design choices, modular payloads, low observability, resilient guidance, and manufacturability combine to produce an effect disproportionate to the size and cost of the system. For defenders, It forces a re-evaluation of layered air defense doctrine. More sensors, more distributed interceptors, and more emphasis on countering the operational patterns such as swarming and deception will be required. For operators, it offers a way to field sustained, adaptable pressure against targets that were previously thought protected by distance or cost. Whether it will alter the broader course of the conflict depends on many moving parts: logistics, training, countermeasures, and political decisions. But as a piece of engineering and battlefield concept, it is a striking example of how asymmetric innovation can reshape modern warfare. If you want to understand the future of strike,